Welcome to part 2 of this VCA or voltage controlled attenuator circuit design and analysis. In part 1 I did the quick overview of the circuit and DC analysis that was posted before, as also shown here on YouTube, in which I evaluated how we can DC bias this circuit and what is the value of, say, the DC of the output voltage depending on the voltage control. Now, in part 2 here, I would like to focus on the AC analysis, which is basically relationship between input and output voltage. Basically, I would like to prove this formula and show how the circuit is working in terms of, let's say, providing an attenuation or gain based on the value of a DC control voltage applied as VC, in which circuit being a negative voltage. I'll talk about that. So at input, we have Vn, which is a, let's say, audio signal, the best application for this example, let's say between 50 Hertz and 20 kilohertz, that's the range of frequency. And then at the output Vout, it generates output signal that has attenuated amplitude, or let's say some scale version of input, in which the scale factor is this factor that is shown here. So we have 2 times Vn divided by 1 plus exp, or e to the power minus v control, divided by alpha plus 1 times the thermal voltage, in which alpha is the scale or coefficient of this resistor here. So basically we have a resistor division for the v control applied at the input of the circuit at this node, and Vt is the well-known thermal voltage for the p-n junction of the BJT transistors that you see in this circuit, in which Vt is well-known kT over Q, K Boltzmann constant, T is the junction temperature for the p-n junction of the bipolar transistors as shown, and in Kelvin, and Q is the electron charge. So we know that Vt, or thermal voltage, nominal value is 25 millivolt roughly for, let's say, when the junction temperature is roughly at room temperature. So when T is roughly 290 Kelvin, or between 290 to 300 Kelvin, so in that ballpark, which means 70 to 27 degrees Celsius for the junction temperature of the p-n junction of the bipolar transistor. So with that said, what I would like to do are these steps. First, I would like to talk about the AC let's say, overview or intuitive analysis of the circuit. So AC intuitive analysis, so that we know what's going on. Then I will start deriving the formulas, so driving intermediate formulas to finally, let's say, get to this formula, which is the final result of the circuit, and also showing how currents are steered. We have 2, as you can see, differential pairs, and depending on V control, which is a negative control voltage, we have the currents that are, let's say, going through the common branch to be steered depending on the control voltage to whether to the left more or to the right side more. So I'm going to talk about that as well, so that we can analyze the circuit. Okay, so let's then start from the AC analysis. We already did the DC. One other note, the control voltage is a negative voltage. There is a variant of this circuit that can basically provide possibility of the positive control voltage with a small change in the circuit. I'm going to talk about that in the third portion of this video. Also, the choice of alpha, which is the coefficient of this resistor that has an impact in the formula, that is something that I will discuss in the third and last segment of this VCA analysis videos. Okay, so with that in mind, let's focus on the AC analysis. Okay, for this electronic gain control or attenuation control circuit, what we have is we have a number of bypass caps or capacitors. These capacitors, let's say, have values in the range of 47 to 100 microfarad, depending on design. And what they do is in the frequency range of interest of 50 hertz to 20 kilohertz of input, they will short or let's say provide a AC ground, AC virtual ground at these nodes. So we have 0 volt here and at this common node, and just again reminding what was already discussed in the DC analysis part 1, negative 10 volt and plus 10 volt are the dual supplies that are used in this design, DC supplies. So from AC standpoint, this node is virtual ground, this node is virtual ground shorted by the cap to the actual ground, which is exactly as the positive terminal of the op-amp. So we have virtual ground AC vice at the positive terminal. Okay, what else do we have? Because op-amps are biased properly, so let's say as discussed in part 1, plus 10 volt, negative 10 volt supply voltage is connected. Virtual short is enforced, and op-amp using based with the negative feedback enforces same voltage as positive on the negative terminal. So we have virtual ground at negative terminal as well, AC vice. Okay, so what is the benefit of that? The benefit is, as you notice, we have V in at the input of the circuit, which appears at this node, and that means across this resistor R, we have V in on one side and virtual ground on the other side, AC vice. So the current that is going this way, let's use a different color. So I'm going to use, let's say, this color. The current I that is going through the resistor R can be easily computed. That AC current I is V in divided by resistor R. So let's keep that as equation 1. Okay, this current obviously can't go to or come from the input terminal of our pump, which has practically infinite impedance. So the only way current can go is this way. All right, so what is the next step? Well, the next step is this node is 0 volt AC vice, so because it's connected to negative terminal of op-amp, which is AC ground. So we have virtual ground here, AC vice, so there is no voltage dropped across this resistor because AC 0, AC 0. So this AC current has no other way than just going up through the collector emitter of, let's say, transistor BJT transistor T5. Remember, this is an AC analysis, so in the DC bias analysis presented in part 1, there is a DC current that is going downward, biasing transistors T1, T2, and T5, NPN BJT transistors. Of course, this DC current is the larger current, so this AC current is smaller than that. We are doing a small signal analysis, and it would just reduce the value of, effectively, reduce the value of total current going down through T5. But AC-wise, it's as if we have a current with this direction going upward through the branch to get to the, let's say, differential pair T1 and T2. If VC or V control is exactly 0, it means similar to the base of T1 that has an AC voltage of 0 volt, the voltage drop across the 100 ohm RA is very small, negligible AC-wise. And as you can see, there is a DC, so AC and DC voltage here at the base are both very close to 0, so I'm writing 0. At the base of T2 and T3 symmetrically, we have just the voltage division of V control applied to this node that goes through a voltage division across these two resistors, RA and alpha RA, and if you compute that voltage division, you simply find the voltage at the base, so V base for let's say transistor T2 will be just 1 over 1 plus alpha times VC, and that's just because of voltage division. I'm going to write it here. So RA divided by 1 divided by alpha RA plus RA, which exactly becomes 1 over, of course, times V control, which becomes 1 over 1 plus alpha V control that I just wrote here. So that's the voltage division. Let's keep that. Now, depending on how negative VC is, if it is 0, of course, then VB2 becomes 0, similar to VB1. So the circuit is exactly symmetric. And as mentioned in part 1, these 4 transistors, NPN BJT transistors, they have to be matched. and therefore they are required to be in the same package on the same substrate. For example, the quad transistors, the quad NPN BJT transistors that are in quad NPN, let's say BJT transistors that are in, let's say, MAT 14, let's say solution that is available from analog devices. There are equivalent products available that can be purchased from, let's say, DigiKey or Mouser, but this is one of the best. Okay, so with that in mind, it's important that we make sure these four are matched BJT transistors. So when we have VC exactly 0, so the base of T2 and base of T1 are both 0, then the symmetricity enforces that half of this current, AC current, will go this way and half will go to the other branch. But when VC becomes more negative, it means it is reducing the voltage of B2 for transistor T2 and also voltage of T3. So more of a current or less of a current is diverted through, let's say, the right branch in the first T1, T2 differential pair. And I'll talk about the same situation happening for the T3, T4 differential pair. At some point, VC, when it is negative enough, it will reduce or it would turn VB2 and VB2 negative enough to turn off T2. If that, at that point, the whole AC current will go effectively to the left branch of this differential pair. Okay, so with that intuition in mind, let's focus on this op-amp. So we talked about the impact of op-amp 1. Similarly, op-amp 2 has the same situation. So the Vin, this is a decoupling, DC decoupling cap or AC decoupling cap. So when AC is there, this is effectively at the frequencies of the signal of interest, 50 Hertz to 20 kilohertz. This cap is short. So Vin is AC Vin is directly connected to, say, via this wire to the positive terminal of op-amp, as you can see. Therefore, we have Vin here, and because of, again, proper bias and negative feedback, virtual short is there for this op-amp, which means Vin will be for negative terminal as well, which is exactly this node. So across this resistor R, we have Vin on one side and AC virtual ground on the other side. So we have a voltage drop plus minus Vin. Therefore, the current that is going, AC current, that is going through this resistor R is the same current I, because its value-wise, its value is Vin divided by R. For the same reason I mentioned, no current can go and come from the input terminal of op-amp because it has practically infinite impedance. Therefore, there is no other way other than coming down from the common emitter node of T3, T4 through the collector emitter of T6 for this AC current that I'm showing. So it's interesting. For the second differential pair, NPN BJT differential pair, the AC current is coming down, while for the first, as was discussed, the AC current is going up. So basically, the AC current is adding to the DC current, and the overall current for these guys, this pair, is increasing, while for this pair is decreasing in the situation when Vin is a positive, let's say, voltage. Of course, when Vin becomes negative, the directions shown will be reversed. Okay, so with that in mind, the same idea happens here. When VC is 0, we have 0 volt at base of T3 matching 0 volt at the base of T4, because the voltage drop across RA is nearly 0, because RA is very small, 100 ohm, and the current is already small. Note that, as mentioned in part 1, these transistors are small signal transistors, and they have large HFE, or current gain, or beta, which is the ratio of collector to base current of the BJT transistors, usually on the order of more than 200, sometimes 400 to let's say 500 even. Okay, so with that in mind, then the voltage at the base of T4 is 0, then V control, when it is 0, voltage at base of T3 0. These are matched transistors, so because of purely symmetric, half of this downward AC current goes through the right branch, half of this downward AC current goes through the left branch. For this analysis, what matters is what portion goes to left branch. Reason for that is, so let's refer to it as I-Y. So I'm going to refer to this left branch current as I-Y, because for this right branch in the first, let's say, differential pair, I refer to it as Ix. The whole current, of course, is I. The whole current is same, is I, according to equation 1, as I mentioned. Reason I care, because the connection is this connection here, the node, because that's the extraction point. As you can see through this wire, we are going to the last stage, which is this op amp number 3, and what is connected to it. That effectively works as a differential amplifier or difference amplifier. And then for the second BJT pair, we have this node that there is an extraction wire from there going to the op amp 3 and final stage at the output. So that's why I care about IY and IX, the portions that are going to this important branches. Okay, so with that in mind, let's find these guys. How do we find them? Let's focus on T1, T2 NPN BJT differential pair. What I can say is from 0 volt at the base of T1, there is a plus minus VBE1. And then from the base of T2 with the voltage, from the base of T2 with the voltage VB2 related to VC with this equation, VC divided by 1 plus alpha, there is a plus minus VBE2 drop. So, and after this drop, we get to a common node at the basically the shared emitter of T1 and T2. So what I can say, effectively sort of like a KVL or Kirchhoff voltage law, I can say because of that, if I start from 0 at the base of T1, and if I subtract the VBE1, I should get to the same voltage, which is the common emitter, as starting from base of T2, so VBE2, minus the, base of T2, which is VB2, minus, let's say, VBE2. Okay, so I am going to use equation 2. So I'm going to repeat that here. So basically, VB2 is equal to V control over 1 plus alpha. So I refer to this as equation 2, just for the ease of reference. I'm going to use equation 2. At the same time, I am going to use the, let's say, Shockley. So let's write it here. Also, Shockley p-n junction equation, which says, so p-n junction, let's say, equation for the bipolar transistor that says the voltage of base emitter of transistor is equal to the thermal voltage that I just mentioned, times e to the power, times log of, natural log of, the current of collector divided by saturation current that is heavily thermally dependent, and we want to get rid of this IS because it's very sensitive to temperature. 10 to 15 degree temperature of the junction change of, let's say, junction of the transistor will result in a huge change in, like on the order of up to 5 to 10 times change in the value of IS. So we want to really get rid of IS. And the way we do that, actually, it's already realized. These guys here is helping us realizing that. How? Okay, I'm going to move this VBE2 to the other side. So I am going to get VBE2 minus VBE1 equal to voltage of base that, using equation, let's say, if I refer to this as equation 3, so combination of equation 2 and 3 is going to exactly give me what I want. So I'm going to substitute here for voltage of base as VC over 1 plus alpha. And then using equation 3, this two guys, VBE1 minus VBE2, becomes VT natural log of current of, let's say, the transistor 2 divided by saturation current, and minus VT, let's say, natural log of IC1 divided by IS equal to VC over 1 plus alpha. Now the benefit is, since these transistors T1 and T2 are matched, then IS is the same and VT is the same for these two transistors. That's why I didn't use different values for them. Now, because of the property of, let's say, log, we can say VT natural log of IC2 over IC1 equal to VC 1 plus alpha. One little change that is going to help me is just invert, let's say, multiplying both sides with a negative sign, and therefore it becomes log of IC1 over IC2. So VT ln IC1 over IC2 is equal to minus VC over 1 plus alpha. Now, one interesting thing, obvious, so let's refer to this as equation 4, and we are almost done for the intermediate formula. One interesting thing, obviously, is, maybe I write it here. You can see that the sum of the AC current of I1 and I2 should be equal to the total AC current that is, let's say, coming upward in this case. So I can just say, and by the way, I'm referring to IC2 as IX, so later on. Okay, so I can just say, therefore, since I am just referring to IC2, so IC1 plus, let's put it this way so there's no confusion, IC1 plus IC2 is equal to the overall current. IC2 is what I refer to as IX. So with that, I can say VT natural log of I minus Ix divided by, yes, that's correct. So I minus Ix divided by Ix equal to minus Vc over 1 plus alpha. And as final step, what I can do here, I can just, let's say, raise both sides, let's say take an exp from both sides, and I get this outcome. I get I over Ix is equal to 1 plus, or let's say put it this way, 1 plus exp of minus Vc over 1 plus alpha times Vt. And of course, what I like to find is Ix, because I is something that is known already from equation 1. So maybe the best thing at this point is just substitute for, let's say, using equation 1 now for the value of I as shown, and then I get Ix is equal to just basically V in over R, so that's the value for I, and I am moving Ix here, and I'm moving this guy to denominator here. So therefore I get that 1 plus exp of minus Vc 1 plus alpha Vt in denominator, and this is exactly what we were targeting, almost there. You can see that I found the target denominator, and it is actually exactly as instructed or as mentioned. We should get there. The only thing that is now as a last step missing is, let's say, translating or converting this Ix, or the portion of current, which is now a function of Vn in the numerator here, into output voltage. So let's do that. That's the last step. That's let's say, derivation step for the final formula. Okay, so this is the fun part. We found Ix now, the steered current toward the target branch, in this case toward the right branch for the differential pair shown here. We just want to see how this translates to Vout, or how this affects Vout. Okay, so let's focus on the connection. This Ix, what is it seeing AC-wise? there is a bypass cap here, let's say 100 microfarad, 47 microfarad to 100 microfarad range. So that for the frequency range of interest, that is effectively short. So it provides a virtual AC ground here. So virtual AC ground. That means this IX current, AC current that is going upward, is going toward this resistor R to the ground, so it results in an AC voltage like this. And also, it's going through this resistor R to ground as well. So effectively what it observes, according to what is discussed here, is what is observing is a parallel of R and R AC-wise. So I'm going to write it here. So I'm going to write that AC voltage at positive terminal of op-amp 3 is equal to contribution from, let's say, IX, effectively, is equal to the parallel of R and R, which means R over 2 times IX AC current. So I'm going to write it here, R over 2 IX. That's the AC voltage at positive input terminal of op-amp number 3 as shown here. Now, the other thing is for IY and contribution of IY to the output as well. So I'll continue we are not yet done with the contribution of IX to the output. We are just at the point that we know what it does voltage-wise, AC voltage-wise at positive input terminal of op-amp 3. For IY, what is happening is, as you can see, again, we are dealing with AC virtual ground on this side, so, and the direction of IY is downward AC-wise compared to upward for IX. That's actually what we really want. They are not, therefore IX and IY are not canceling out each other because of counter direction they have. So let's see. So there is, I can write it this way now to help understanding what is going on as the last step. V out has some coefficient multiplied by, let's say, the contribution of IX, plus V out has some contribution from, as you can see here, from the IY. So in order to find these coefficients that result in final output voltage, I'm going to use superposition. So the superposition, so using superposition, I would say here, so using superposition, in the sense that I'm going to make the assumption to find these guys. I'm going to make the assumption that once IY is 0, is not there, and figure out the contribution of IX, and for IY and its coefficient, I'm going to make the assumption that IX is 0, not there, so that I find them. First, for IX and its contribution, assume IY is not there, so as if IY is 0, which means, effectively, which means this is open. So let me just show it. It means as if this is open and we have this connection, for example. So the circuit looks like this. So from the perspective of op-amp 3, what it looks like is a connection from output through this resistor to ground. That's it. So effectively, since we have a voltage at positive terminal, from perspective of what we generated at the positive terminal, the circuit looks like exactly like a non-inverting amplifier for the third stage. So I am going to exactly sketch that here. Okay, so the circuit looks like this. When, let me write it this way, so just to make sure you can see what I'm writing. So when IY assumed to be 0, we get, let's say, the third stage, op-amp stage. The third op-amp stage looks like, and it is a non-inverting amplifier. And it looks like exactly this scenario. So we have the op amp number 3 at the positive terminal. We have this voltage. So we have R over 2 times Ix voltage. So this is volt. And then negative terminal, we have a connection through a resistor R. So through a resistor R to virtual AC ground and a feedback resistor R. This is a simple non-inverting amplifier, and it's super easy to just use a KCL to show that the output voltage contribution by this input voltage is simply the input voltage, which is R over 2 times Ix times 1 plus feedback resistor R. So feedback resistor R divided by this resistor R. So it means 2, which then cancel out with the 2 here in the denominator, and therefore the contribution Ix to output is just R times Ix. Of course, we need to be careful. So what we get in this scenario is the contribution of Ix to the output. So all I'm saying is this coefficient turned out to be 2 here. Times R over 2 Ix. Okay, so we found the contribution of Ix. Or if you're more comfortable, I can push this R over 2 inside here, and then I would write 2 times R over 2, in which 2 and 2 cancel out each other. Which basically, I mean, in a most, let's say, accurate way, I can put it just here, exactly as I wrote here. So multiplied by Ix, of course. So we have this whole thing becoming equal to 2. All right, what is the next one? The contribution of Iy. So for Iy, I am going to write here when Ix is set to 0 using superposition. Let's see what's going on. So this time we are setting Ix to 0. As a result, what happens is this current is not there, which means this branch is open. So we have this connection, and therefore we have Iy. But what is the meaning of this connection when no current flows through it, because it's only connected to positive terminal? So effectively, that means there is nothing going through this resistor or this resistor. So if on the other side of these resistors, we have pure AC ground and nothing is going through them. There is no voltage drop through these resistors. And therefore, what happens is we have 0, or we have basically virtual ground at this node, which means at the positive terminal of op amp number 3, we'll end up having virtual ground, 0 volt AC bias. So now what happens is Iy is injected to the circuit, and at this node we have 0. Because we have 0, because op amp, of course, being a properly biased op amp with negative feedback, it enforces same voltage at the positive and negative terminal, virtual ground. So if we have 0 at positive terminal, we have 0 at positive terminal as well, at negative terminal as well. So on both sides of this resistor R, we have 0. That means this incoming Iy can't go through R. This Iy with this direction can only come from the resistor R shown here. That's the beauty of this circuit. So that means it results in a voltage drop across this resistor R times Iy. That's the conclusion we have here. So R times Iy is the outcome there. So basically, because this node at the negative terminal is 0, and we have a R times Iy voltage drop across R, that means the output voltage contribution will be just R times Iy. So with that said, I am going to just write the contribution. So let me just clean up the circuit. Okay, so with that said, we have R times Iy. Then the circuit becomes effectively like this. As I said, we have current Iy, we have a resistor R that is connected to virtual ground, but this node is also ground. So, and then connected to connected to negative terminal via wire like this, in which this is op-amp 3, for which the positive terminal is virtual ground AC, and then we have this resistor R to the output voltage. So this current Iy, can only continue this way and will result in a voltage drop plus minus with that direction, and V out becomes R times Iy with the polarity that is shown versus the virtual ground that is at negative terminal as well. Okay, so we found contribution of Iy to the output. That's just a scale of R resistor. And we found the contribution of Ix to the output. That is also a scale of R resistor effectively. So all I can say in summary, when I put together both contributions computed using superposition, I get V out is Rix plus Riy. Of course, with the consideration of the directions I showed. Ix and Iy equal to each other. There is no difference. Circuit is symmetric. So whatever happening is in a sort of a mirror symmetric fashion with respect to this center line is happening to whatever happening to the first differential BJT pair is happening to the second differential BJT pair. So obviously Ix and Iy equal to the same value that is shown here. So I computed the formula for Ix in equation, let's say 5. So this is the super important equation 5 here. That is the same thing for Iy as well. So Ix and Iy, they are equal to each other. So as a result, I can just say V out is 2 times R times Ix. And then using equation 5 that I just showed, I substitute for Ix, and then 2 times R is going to multiply numerator, which is V in over R, and that will give me just 2 times V in. So I get V out equal to 2 times V in divide by, so if that is not clear, 2 times R, V in over R, and R is cancelled out with R, so we get 2 times V in. And denominator is 1 plus EXP of minus V control divided by 1 plus alpha times the VT, which is the thermal voltage of PN junction of the bipolar transistor. This is the final equation we found for the output voltage as a function of input voltage, and basically the scale is as we talked about. So the scale is this whole thing with a factor of 2. I hope that this AC analysis of the let's say the VCA circuit in this part 2 is helpful to show how this circuit is working and what are the nuances involved in the AC analysis of this interesting and I would say beautiful circuit that use combination of, say, op-amp and matched BJT transistors using 2 differential pairs, and of course 2 other NPN transistors that are serving as the current injectors. And then V controlled is serving as a control voltage, negative control voltage that is steering the current away from T2 and T3, and therefore generating an attenuation in the circuit, because by steering away, we are reducing the amount of the current that is flowing toward the final stage. And as we make VC more negative, we are steering more current away from the output stage, and therefore we will reduce the Vout. The control is in a nonlinear fashion, but it has a lot of application in audio signal processing and similar examples. This is the end of part 2. So part 1 was DC analysis and overview. Part 2 is this AC analysis and proving the formula. In part 3, which will be hopefully a brief segment, I'll talk about the choice of alpha here. So basically the choice of alpha for this resistor RA that is impacting the denominator of the output of the formula. And also I'll talk about a little variation that would enable positive voltage control, let's say compared to this method here that is requiring a negative voltage control. I hope this example is helpful. Again, the link will for the part 1 is below this video, and then the link for part 3 will also post that soon. Thanks.